We have just learned how the molar Gibbs energy of a pure substance depends on the variables pressure and temperature. What we're going to be explaining now is how that molar Gibbs energy depends explicitly on only the pressure. Okay, so we're going to be concentrating on just the pressure and not the temperature. All right, this is the general expression for the dependence of the Gibbs energy on pressure and temperature, but to focus exclusively on pressure, we're just going to make the temperature constant, and what that means is that differential of T will be 0, again if we keep the temperature constant, and then we can erase this term. Okay? Another way to write this dependence of the molar Gibbs energy on pressure is to simply say the following. The first derivative of the molar Gibbs energy with respect to pressure is going to be equal to the molar volume, V sub m, but this is at constant temperature. Okay, so what is the molar volume? The molar volume is simply the volume occupied by 1 mole of the substance in whatever phase it is. For example, for water, we know that the volume of 1 mole is about 24 liters. Okay? But if we go to the liquid phase, that volume gets reduced by about a factor of 2,000, and it's only 18 milliliters. And for a solid, it's very close to that of a liquid. Okay, so what we actually see is that, well, whatever the phase is, this number is always positive. It's always the volume of 1 mole in whatever phase you are. Okay, what that tells you automatically is that if this number is positive, then if you increase the pressure, that means you make that differential of P positive. If you increase the pressure, then the molar Gibbs energy has to increase as well. Again, because the molar volume is positive. Okay. So then, what we actually can do here is, in addition to writing this expression, we can start to draw a little graph that tells you how this happens. Right. So we can plot the molar Gibbs energy versus pressure. And again, notice that because we're examining here first derivatives, okay, the slope of this molar Gibbs energy with respect to pressure is going to be exactly the molar volume. Okay, so what we'll have is that because the molar volume of the gas is very large compared to the molar volume of the liquid or the solid, the slope of the gas line is going to be very, very steep, and those of the liquid and the solid are going to be not so steep. Right, so we can draw here that this is going to be the equation for the gas, this is going to be the variation of the molar Gibbs energy for the liquid, and this is going to be the variation of the molar Gibbs energy with pressure for the solid. And again, at any point, what we actually have is at the slope, this molar Gibbs energy versus pressure at constant temperature is going to be equal to the molar volume. Okay? All right, so there are a lot of things that emerge from this graph which are very interesting. Okay, for example, notice that for this particular substance, if we increase a lot the pressure, then what happens is that the stable phase is the solid. Okay, why is that? Well, notice that at this particular condition, at this pressure, the line of the solid is below that of the liquid and the gas, and these lines represent the molar Gibbs energy. Well, we know that of the 3 phases that we're studying here, the one of lowest molar Gibbs energy is the one that is going to be stable. So again, at high pressures, we see that the line that is lowest of these 3 is that of the solid, and that means that the solid would be the stable phase. We can go to the other range of pressures, right? Very, very low pressures. That means that we're applying a vacuum. Okay, well, at low pressures, what we actually see is that the stable phase is the one of lowest molar Gibbs energy, and that seems to correspond to the gas. Okay, and at intermediate pressures, what you actually have is that, well, the liquid is the stable phase. Okay, so this actually is very interesting because it tells you that you can control the stable phase of a substance with pressure. Okay, at constant temperature. Okay, again, notice that in this range, at pressures higher than this dashed line, you will have that the solid is a stable phase. Here will be the liquid is a stable phase, and at lower pressures, you will have that the gas is a stable phase. Okay, so this is kind of a new concept for many of you. We know that we can change the phase of a substance by changing the temperature. For example, you can denature a protein thermally by increasing the temperature. What this tells you is that you can also denature a protein. You can change the stable phase of a protein changing the pressure. And we actually know that that happens in reality. Applying a lot of pressure to a protein will denature it in many cases. And again, you can prove how that is the case with simply this expression. Okay? Now, for the rest of this section, what we're actually going to do is try to work a little bit through these expressions so that we can actually do numerical problems that test explicitly how the molar Gibbs energy changes with the pressure. Okay, so let's see how that works. All right, so notice that what I have drawn here is the fact that the liquid and the solid lines seem to have a constant slope. Okay, but the line of the gas, you can see that the slope is changing. Okay, so why is this? Well, we know that the slopes are related to the molar volume. What this is telling you is that the volume occupied by 1 mole of liquid or solid doesn't change much with pressure. And we know that that's the case for liquids and solids because, again, you can have a glass of water, apply pressure, and the volume is just not going to change, right? So liquids and solids are highly incompressible. And again, the volume of 1 mole or a given amount will not change much when you apply pressure. That's not the case for a gas. Think about a gas put into a cylinder. Well, when you apply pressure to that cylinder, you can clearly change the volume, right? So that tells you that where this variation comes from. Okay, liquids and solids are incompressible. The volumes don't change much with pressure, but that's not the case for a gas. All right, great. With those notions in mind, again, we can try to solve how this expression would work for a gas. So let me erase this graph and see how this applies. Okay, so for a gas, what we have is that differential of Gm is going to be equal to the molar volume differential of P. Right, but for a gas, what we actually know is that, well, under ideal gas conditions, we can always apply this expression, which is the ideal gas equation of state. The molar volume is simply volume per mole. Okay, so this is equal to V sub m, which is equal to RT over the pressure. Okay, so then we can write here that that is simply going to be RT over the pressure differential of P. And this is nice because it's going to allow us to actually integrate an expression and find an explicit dependence of how the molar Gibbs energy changes with pressure that we can use in problems. All right, so integrating this, we simply get to the following. The integral differential of Gm is this delta Gm, and the integral of RT differential of P over P from P1 to P2 will be the following. R and T are constants. Notice that in all of these problems we're holding the temperature constant. Okay, so this is going to be equal to RT, the natural log of dP over P, and we've seen this integral many times before this semester. This is simply equal to RT natural log of P2 over P1. Okay? This equation tells you explicitly how the molar Gibbs energy changes when you change the pressure. Okay? Notice that there's a logarithmic dependence between the Gibbs energy and the pressure, and that's why this line for the gas that we were drawing before, okay, molar Gibbs energy versus pressure, had a curvature to it. That's a logarithmic dependence. Okay? All right, so we will be using this expression in numerical problems in the homework, and you have an illustration also in the book. All right, what about for solids and liquids? All right. Solids or liquids? Well, we have the same expression that we can integrate. Differential of Gm is equal to Vm differential of P. Now, there's two things that are important about this Vm. One of them is that we actually don't have an expression that is as nice as the ideal gas equation of state to be able to write what that molar volume is. So either the problem has to give us the actual molar volume, or we need to find a way to calculate it, maybe with the density and the molar mass, and we will learn how to do that in the homework as well. But the other important thing is that this thing is constant. Again, we're assuming that the molar volume doesn't change when you apply pressure to the solid or the liquid. So integrating this, then what's going to happen is that, well, this is a constant number, so then we can integrate it out. Okay, when you integrate that, then that is going to be delta Gm is going to be equal to the molar volume of the liquid or the solid multiplied by the integral of differential of P from P1 to P2, but that is simply going to be delta P. Okay? And again, notice how that tells you that the variation of the molar Gibbs energy with pressure is just going to be a constant. Okay, that slope is simply going to be a constant number, which is just the molar volume. And again, we will learn how to operate with this expression in the homework, and you do have an illustration in the book.